Welcome to Math341, lecture 17, I think. So what we're going to do today is we're going to do sums of random variables. We'll start off with sums of uniform random variables, which we've already done a little bit with. And then we will go to sums of Gaussian or normal random variables. To keep the notation manageable, we will often work with special cases. We'll assume the mean is 0. We'll assume the standard deviation is 1. You need to be comfortable enough with your calculus to do the change of variables. And these are going to be very simple translating and rescaling. Okay? So, sums of uniform. So we've already seen sums of uniform random variables. Right? If you have a die and just roll it, you get the numbers 1 through 6. Each one occurs 1/6 at a time. And I remember writing out in great detail like a triangle like this of what happens if you roll 2 for your die and you look at the sum. And you have one way of getting 2, one way of getting 12. 2 ways of getting 3, 2 ways of getting 11, all the way up to 6 ways of getting 7. And you see that for 2 die, it looks like this. It'll be the discrete version of this. But this gives us some intuition for what we would expect if we now sum 2 uniform random variables. I might expect something like this. Whenever possible, use symmetry. Nice job. Use symmetry to try to minimize how much algebra you need to do. Okay? Whenever possible, look at small cases and build intuitions. So with that intuition, let's say x1 and x2 are uniform on 0, 1. And let's let y be x1 plus x2. What do you expect is true about this random variable y? Symmetric. Symmetric about what? So it's symmetric about what?
The mean.
Which is?
The mean of x1 and x2.
So what's the mean of y? Symmetric about? About 1. Since x and y are uniform on 0, 1, they both have mean 1/2. So the expected value of y is the expected value of x1 plus the expected value of x2 will be 1. So we expect the random variable y to be symmetric about 1. Here's a quick proof. Let's let wi be 1 minus xi. And then w1 plus w2 is really the same as x1 plus x2. If I look at the distribution of w1 plus w2, the important thing to know is each w is also uniform on 0, 1. So the sum of w1 plus w2 is got to be the same distribution as the sum of x1 plus x2. And really, if I give you a pair x1, x2, the w pair would be 1 minus x1, 1 minus x2. And you can use this to show that the distribution will be symmetric. Okay, so let's do the calculation. So we want to find the PDF of y. I will, for the most part, just concentrate on calculating the PDF of y for values between 0 and 1, because by symmetry, I know what's going on for the rest. If you don't see the symmetry argument, what can you do? If you don't notice that it's symmetric, what would you just do? Well, we're doing the convolution anyway. You just keep calculating. Right? So if you ever miss a symmetry argument, it doesn't mean it's game over. It doesn't mean you can't get the problem right. It just means you have to do a little bit more algebra. But if you notice some symmetries, you can often cut down on how much algebra you need. The last time I taught this class, I was looking at my notes. I had a conversation with a colleague right beforehand about, do we need parabolists in the 21st century? Why should we do this? Let's just simulate, right? Generate a couple of trillion values from a uniform, sum them, and see what happens. This is one of the powers of statistics. Well, the real power of doing all of this is getting a closed form expression. If you can have a closed form expression and you can explicitly see how things vary when you change the parameters, that is terrific. Okay, and that's what you really want to be able to do. And so this is one of the themes of the class, is every now and then we are fortunate enough to get a closed form expression. For certain problems like this, you will quickly realize you do not want the closed form expression. We saw very early in the semester what a sum of 4 uniforms looked like, and I didn't even bother writing down what it would be for 8. It becomes unwieldy. Then you do the next major theme of the class. Rather than getting a closed form expression, you get a good approximation to the truth. And that's where the central limit theorem will come into play. So we want to calculate the probability that y is at most little y. And by definition, this is going to be so x goes from minus infinity to infinity, and then y goes from minus infinity to y minus x. The density of x1, x2. x1 of x1, the density of x2, dx2, dx1. So this is the high-level start, where what's the probability we take on a value at most little y? Well, if x1 takes on a certain value, then x2 can be at most y minus that little value. And we saw this led to, this is the cumulative distribution function. If we take derivatives, we get the density. And this is just the integral x1 goes from minus infinity to infinity, f of x1 of x1, f of x2 of y minus x1 dx1. So this is the convolution. The way you see this is we first integrate with respect to x2, and we get the cumulative distribution function at y minus x1 minus the cumulative distribution function at negative infinity. The cumulative distribution function at negative infinity is just 0. When we take the derivative, the cumulative distribution function at y minus x1 becomes just the density at y minus x1. So this is the convolution. Initially, it's going from x1 goes from minus infinity to infinity. But we know these are uniform random variables. So what's the first thing we can simplify? So what can I do for my range of integration?
Set it to 0 to 1.
Yeah, so this is the same as x1 goes from 0 to 1 of f of x1, x1, f of x2, y minus x1, dx1. I just want to go through, yes?
Also, isn't f of x2 the same thing?
Yes. Yep. So these are both the same. And now, what do we know about f of x1 in this range? Since it's a uniform on 0, 1, what is the density equal in this range?
1.
Yeah, it's just 1. So this is just the integral x1 goes from 0 to 1 of f of x2 y minus x1 dx1. So this is only going to be contributing if the argument is between 0 and 1. So we need 0 less than equal to y minus x1 less than equal to 1. So we get x1 is less than equal to y, and y minus 1 less than equal to x1. And yes?
Can you explain how you change the balance just one more time?
From here to here?
Or one more down.
Sure.
Oh, yeah, I guess. Yeah.
Because I have a uniform random variable. It's uniform on the interval 0, 1. So because it's uniform on the interval 0, 1, the density is just equal to 1. If I had a more complicated function, I couldn't put in a 1 here. But really, there's a 1 floating here. And so now, things become a little bit annoying. It depends on what y is as to whether or not this is a restriction. If y is equal to 1.5, this is no restriction on x1 at all, because I already know x1 is between 0 and 1. So if y is larger than 1, this restriction does nothing. If y is less than 1, this is a negative number. So in fact, only one of these restrictions ever matters. Okay? And so now what we do to finish the analysis is we break it up into two cases. Whether or not y is greater than 1 or whether or not y is less than 1. So if y is less than or equal to 1, only x1 less than or equal to y matters. And then we would get it equals the integral from 0 to 1. X1 only goes up to y, so now we would change this to a y. F x2 of y minus x1 dx1. But now, what is this density equal? So x2 is a uniform random variable in 0, 1, so what does that density equal? It just equals 1. So this becomes integral from 0 to y of 1 dx1. I have to work hard to give you an easier integral than this. Right? You're integrating the constant function 1 from 0 to y, you just get y. And so now we know the density function is equal to y if 0 less equal to y less equal to 1. We know it's symmetric about 1, so you can use that to figure out what's going on the other side, or you could just do the other stuff. So I'll leave the rest as a calculation. But you will get the density will look like this. Here's 0, here's 2, here's 1. And it's going to be a triangle of height 1. If you remember how to calculate areas of triangles, you will see that the area, the basis to the height is 1, 1/2 base times height. Great. Why am I calculating the area of the triangle, other than the fact that I love triangles? Good, if it's not 1, we've made a mistake. If you can ever do a simple check and see, is this right, please do so. Okay? And so because the area is 1, we're in pretty good shape. So the question is, can you write this in a nice closed form? So maybe if you did 1 minus the absolute value of y minus 1, I think that would work for the density. And notice that this is clearly going to be two straight lines. When y equals 1, you get 1. When y is equal to 0 or 2, you get 0. So that's an explicit form of the density. I don't have to do the second integral by symmetry. This is not a horrible form. It gets worse as you do more and more and more. Okay? Any questions on the sum of two uniform random variables before we move on to more uniform random variables? Okay. So I'm not going to do the next one in great detail. We've talked a little bit about this. Do I want to do 3 or do I want to do 4 uniform random variables next? I want to do 4. Because I can group things. So if I have each xi is uniform 0, 1, if I do x1 plus x2 plus x3 plus x4, if I group them like this, I know what this density is. This is going to be my triangle. And this will be a triangle. So I'll have triangle convolved with triangle. And then after doing 4, what would I like to do next? 8. And as an exercise, if you want, you can use Mathematica, write down, I'll make this worth a homework exemption, because I know people were gunning for a homework exemption today. Give me the closed form expression for the sum of 8 uniform random variables. So you can program Mathematica to do this. Whether or not Mathematica will finish the calculation, I'm not sure. Sometimes it gets a little finicky and does not want to do some of the algebra. But I think you could probably get it to work out. And just see how bad it is. And if you don't feel that it's bad, do 16. And at some point, hopefully you will realize that you do not want to work with this. And that's why we have the whole idea of the central limit theorem and approximations. All right. Any questions on sums of uniform random variables? So this was a great way to see the convolution come into play. I wanted to take the time and start off with, where does this convolution formula come from? This is one of our most important formulas. It comes from the CDF method, of calculating what's the probability we are at most little y, then we take derivatives, and blah, 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 blah. All right. We are now going to go to normal. This is probably the most important distribution in the course. So sums of normal random variables. All right, so for my people who have taken stats, how many of you have heard of stable distributions? Not many. All right, so a distribution is stable if its shape does not change if you add a copy of itself to itself. So for instance, is the uniform stable? Is a uniform plus a uniform a uniform? No, it's a triangle. It turns out normal random variables are stable. Normal plus normal is normal. Is it possible that the sum of two normals has the same mean? Yeah, so let's say xi is normal mean ui variance sigma I squared. And let's let y be x1 plus x2. Is it possible for mu y to equal mu x1 plus mu x2? I'm sorry. Mu y equals that. Could this equal mu of x1? Yeah, if the means is 0, then you could have the mean of the sum is the same as the mean of the initial. So we know that the mean is the sum of the means, and it's possible that your mean is not changed. If I gave you two uniforms, if instead I had the uniform centered at the interval going from, say, minus a half to a half, then the sum of the uniforms would also have a mean of 0. What about the variance? So sigma squared of y, it's the variance of x1 squared plus the variance of x2 squared. Can that equal the variance of x1 squared? No. You would have to have it completely collapsed. The variance is going to grow. So if you wanted the sum of two copies of the same distribution to be exactly the same distribution, this would be a boring subject. The only thing that would work would essentially be point masses. So instead we weaken it and say, look, they don't have to be the same distribution with the same values of mean and the variance, but they have to have the same shape. So if I want the sum of two normals to be normals, it doesn't have to have the same mean and the same variance. But it can't be an exponential. It can't be a y-able. Now, if I want y to be a Gaussian, there's only one Gaussian it could be. And the hope is that y is normal with mean mu1 plus mu2 and variance sigma x1 squared plus sigma x2 squared. And as an aside, when we're writing means and variances for the normals, we have this notation mu I sigma I squared. How many of you have ever wondered why are we writing the variance rather than the standard deviation here? All right, no one's really been curious about the notation. This is the main reason why. Because if the second argument is the variance, when we add two normals together, we just have the sums of the variances. If this was the standard deviation, you would then have to put in square roots over here, and it would make things a lot nasty in terms of writing. This is at least my belief as to why we have chosen to denote the normal distribution with parameters mu sigma squared rather than parameters mu and sigma. This is the point where it now starts to make things nicer. Well, fortunately, this lecture has been carefully prepared, so we get right back to this board exactly when we need. And there were some questions earlier about, well, don't we know what these distributions are? Why are we writing it as f of x1? To just see how little changes as we go from sums of uniform to sums of normal. All right? Find the PDF of y. Starts off exactly the same way. Probability y less equal to y is the following integral. That is exactly the same as before. All right? We take the derivative. We get the convolution. Exactly the same as before. Now things start to change. We're not going to drop it down to 0, 1 and replace this then with 1 because it's uniform. So what's interesting now is any value can happen. No matter what x1 is, I can always take a value of x2 to be sufficiently negative to pull it down to whatever I want. So the integration is going to be a lot more involved. Okay? I have deliberately not looked at the calculations because they're boring and I don't want to have to look at them twice today. So please be following the algebra to see if I'm making any mistakes. Let's assume mu1 equals mu2 equals 0, sigma 1 squared equals sigma 2 squared equals 1. This will just simplify the algebra a little bit. If we can do this case, we should be able to do the more general case and just adjust things. So we're going to get to one of my favorite techniques in all of probability. So what's one technique you know I love? Differentiating identities. This is another great one. It's called the method of the normalization constant. If I give you a probability distribution, it must integrate to 1. So imagine I give you something, and I know it looks like e to the negative x squared over 2. And I have some constant. This looks a lot like a Gaussian. It looks like a Gaussian with mean 0 and variance 1. So this would force c equal 1 over square root of 2 pi. So frequently, if you can get the functional form, and you have everything up to a constant, you don't actually have to do the final integration. You know it has to be whatever is necessary to make it equal 1. Now, that means you can't use the fact that it integrates to 1 as a check to make sure you haven't done any algebra right. You're now forcing it to integrate to 1, but that's all right. For a lot of these, you would much rather avoid doing the terrible integration than check and make sure you haven't made a mistake in the terrible integration. So let's write down explicitly what we need to compute. We need to integrate x1 goes from minus infinity to infinity, 1 over square root of 2 pi, e to the negative x1 squared over 2, and we're going to have e to the negative y minus x1 squared over 2. We have another square root of 2 pi, so this becomes just a 1 over 2 pi dx1. All right. So this is the integral we need to do. All right. So when you look at things, we've got x1s, we've got y terms, and the y terms do not have any x1 dependence. We can just pull that out of the integration. So let's look and see what we have. I'm going to look at the integrand. So I have e to the negative x1 squared over 2, and then the other one, if I expand things out, will be e to the negative y1 squared over 2. Then I'm going to have plus 2 x1y over 2, so it'll be a plus and x1y, and then it'll be a minus x1 squared over 2. All right. So I'm going to write it as e to the negative y1 squared over 2. I'm going to just pull this out of the integration because this has no x1 dependence. And oh, look, this is looking a lot like a Gaussian. Unfortunately, I still have some y's left, and I'll have an e to the negative 2 x1 squared over 2 plus 2 x1 y1 over 2. I'm just leaving the 2's down below because I know that's going to be useful in the next step. All right. E to the negative y1 squared over 2, e to the negative 2, and I'll have x1 squared minus x1 y1 divided by 2. All right. This is meant to be highly suggestive the way this is written. Okay, so I get my negative 2 x1 squared over 2. Good. I've got negative reinforces. What is this looking like in here? So this is the hardest part of the algebra.
You want completing the square?
Yeah, we want to complete the square. Right? So we've got a squared minus twice, so I could write this if I wanted as minus 2 x1 y1 over 2. And so what I would want to do add in x1 y1 over 2 squared, and then subtract x1, y1 over 2, almost left enough room, squared. Did I make a mistake?
No, just one.
Just y1, thank you. Then I would have had enough space if I had done it like that. All right, thank you. Okay, I knew there would be an algebra mistake. All right? So now when we look at this, we're going to get e to the negative y1 squared over 2, e to the negative 2. Now this whole thing over here becomes x1 minus y1 over 2 squared over 2. And then a minus and a minus becomes a plus, right? And we'll have an e, the 2's will, well, leave it like this, e to the 2 y squared over 4. So I think it's just y squared over 2 when the dust settles. So I've got a 4, an 8, and a 2. Okay. That doesn't look right. It should be y squared over 4. Right, because when I square this, I get a 4 here, and then the 2's cancel. All right, so now I can move this and combine that with this, and I'll get an e to the negative y1 squared over 4. And e to the negative 2 x1 minus y1 over 2 squared over 2. So this was a bit of an algebra aside. But the whole point now is that is looking a lot like a Gaussian. And over here, I'm going to integrate this. x1 is going to go from negative infinity to infinity. Well, what does this look like? This looks a lot like a normal. Now I have to identify what is the mean and what is the variance. But does the y1 dependence really matter? I'm just translating the whole thing. So when I come back now and I substitute that in, I get the density of y is going to be 1 over 2 pi e to the negative y1 squared over 4 integral x1 goes from minus infinity to infinity e to the negative 2 x1 minus y over 2. I don't know why I'm calling this y1. It should just be y. Y over 2 squared over 2 dx1. So the thing to note is, all I've done is I've just translated x1 by y halves. When I'm trying to calculate the normalization constant for normal, the mean doesn't really matter. It's the variance that matters. I can change variables. Let's let t be x1 minus y halves. This is the same as 1 over 2 pi e to the minus y squared over 4 integral t goes from minus infinity to infinity e to the negative 2 t squared over 2 dt. The whole point is, I could actually figure out what this is. I could figure out what normal it is. But it's just a constant. This is some constant. No y dependence. It doesn't depend on y. So I get some constant over 2 pi e to the negative y squared over 4. Okay? How should I view the number 4? There's lots of different ways of writing 4. I should write it as 2 times 2. So that's good. There is a slightly better way than 2 times 2. 2 times... Yeah, that's even better. C over 2 pi e to the negative y squared divided by 2 times the square root of 2 squared. Why would I do this? Because now this looks like a normal with mean 0 and standard deviation squared of 2 or variance 2. That's my sigma squared. So this is where the functional form lives. So this normalization constant over 2 pi has to be whatever I need to make this work as a normal with mean 0 and variance 2, or mean 0 and variance square root of 2. And so I will erase this so everybody's good with the method of completing the square. Goes all the way back to the quadratic formula. We get to use that again. So we get that x1 plus x2 is a normal with mean 0 and variance 2. And this was the case where mu1 equals mu2 equals 0, sigma 1 squared equals sigma 2 squared equals 1. And if you want to be explicit, the normalization constant, well, we have an e to the negative y squared over 2 times square root of 2 squared. So it's going to be 1 over square root of 2 pi sigma squared, which is 2. And that's the explicit form. If you had wanted to do the integration explicitly, you could have done that and you would have had this, but there was no need. And we are going to see a truly tremendous application of this when we look at chi-squared random variables. I think that might be Wednesday's lecture. And we will be able to get from this the surface area and the volume of the n-dimensional sphere without having to use hyperspherical coordinates. Given how much enthusiasm there was when we did polar coordinates, I can only imagine what would happen if we went to spherical or yeah, I'm seeing the, yes. Oh, that's the day I have to get sick and have the unnecessary surgery, right? Yeah. I know nobody wants to see that stuff. It's wonderful that you can bypass all of this. Right, any questions on what we've done? Yes?
Did you just sort of know that, like, the f sub x1 for a normal variable is equal to...
Yes, yes. So we're now explicitly substituting in the densities. So up to here, the calculation is always the same. If you think back to Calc 1, when you proved your differentiation rules, the derivative of a product, the derivative of a quotient, the derivative of a sum, you always start with the definition of the derivative, and you have some function a of x is maybe f of x plus g of x, or f of x times g of x, or f of x divided by g of x. And you write down the definition of the derivative, you substitute it in, and then lots of algebra. It's the same thing here. It's always the same up to here, and then from this point onward, now we start to substitute. Now we start to figure out what are the boundaries. Now we start to do the algebra, and hope at the end of the day we can get something nice. Yes?
So when we are substituting by t, how do we know the upper bound and lower bound is still infinite and minus infinite?
Well, so we're letting t be x1 minus y over 2. Remember, y is fixed. So since y is fixed, as x1 goes from minus infinity to infinity, t will go from minus infinity to infinity. And dx1 will be the same as dt. So the way you really want to think about this is, I have a normal here, and I'm just translating the whole thing. That's not going to change the area under the curve. If I just translate, the area doesn't change. If I rescale, if I compress the real axis or I expand the real axis, that will change the area under the curve. But because this is a simple translation, there's going to be no change. Okay. Any other questions on this? So you could now add 3 normals or 4 normals. And in fact, because we know the sum of 2 normals is normal, we can actually do things a lot easier than we can with the uniform. So with the uniform, oh god, it's a triangle. So if we want to do 3 uniforms, it would be a uniform plus a triangle, and we would have all of these painful things to do. But with normals, so let's say xi is normal, mean ui, variance sigma I squared. And we want to do x1 plus x2 plus x3 plus xn. The first thing is we can add these and get x1, 2 plus x3. And for x1, 2, it's going to be normal. What's its mean? mu1 plus mu2. And what's its variance? Sigma 1 squared. And now we add x1, 2, and x3, and we will call this x1, 2, 3. And its mean will be mu1 plus mu2 plus mu3. And its variance will be the variance of the first one plus the variance of the second, so it will be sigma 1 squared plus sigma 2 squared plus sigma 3 squared. And from this you can see, there's a theorem that we can extract from all this. And so this is much, much better than sums of uniform random variables. And so in this case now, we get as a theorem, if xi is normal, mean mu I, variance sigma I squared, then x1 plus xn is normal with mean mu1 plus mu n and variance sigma 1 squared plus sigma n squared. Really nice results. It's the power of stable distributions. Because the shape doesn't change when you add two normals to each other, it makes this calculation very nice. Does anybody know any other stable distributions? I know two others. One of them is actually often viewed as a bad distribution, but it does have a nice property here. The Cauchy distribution. The easiest way to prove the Cauchy distribution is stable is, I think, to use complex analysis. I believe you can do it without using complex analysis as well. But Cauchy plus Cauchy is Cauchy. And it turns out that in some sense, the Cauchy distribution and the normal sit in a family of distributions together. So after every lecture, there's additional comments you can read about the lectures. The ones for today talk about Mandelbrot and the fractal misbehavior of markets. His hypothesis was people are doing a terrible job when they model stock markets by flipping coins and using a random walk. It doesn't have enough days of large fluctuations, both good and bad. And that when you use something like a Cauchy distribution, that actually does a better job. So if you're interested in stuff like this, let me know. There's a lot of stuff I can give you to read up on stuff like this. But this is phenomenal that the Cauchy and the normal can in some sense sit in a family together. There is another one, the Levy distribution, but that's much harder to work with. All right. So what I want to do for the rest of today is just start talking about properties of the gamma function. So we need the gamma function for several reasons. One is it is one of the key ingredients in the normalization constants of chi-squared random variables. We will also use it for Stirling's formula, which will help us lead into the central limit theorem. All right, the gamma function. So gamma of s is the integral from 0 to infinity of e to the minus x to the s minus 1 dx. And you can also write that as e to the minus x to the s, dx over x. So if you continue in mathematics, you will see this is a good way to think about things, because if I rescale x by a factor of 5, dx over x is unchanged. So this is invariant under rescaling by multiplicative constant. This is to try to motivate why we have it defined with an s minus 1. A nice fact is you can compute a lot of these. Have we computed any of these in the class yet? I think we did it briefly. So you can get gamma of 1 is 1, gamma of 2 is 1, gamma of 3 is 2. It looks like it might be the Fibonacci numbers, but then you see gamma of 4 is 6, gamma of 5, 24, gamma of 6, 120, gamma of n plus 1 is n factorial. So it's a little bit annoying that it's offset by 1. The first thing, whenever you see an integral, is you want to make sure is the integral well defined. So when you look at this, the fact that I have an e to the negative x, that's really good as x gets large, because this is exponential decay. So at infinity, I'm not worried. This is at most polynomial growth. Exponential decay kills polynomial growth. How many of you have seen those calculations using like L'Hopital's rule to show that how many of you have not seen exponential decay kills polynomial growth? All right, let me just quickly sketch this. let's look at e to the negative x versus x to the 20. I'm going to show that e to the negative x decays so much faster than x to the 20 grows that we're okay. All right? Let's compare x to the 22 over e to the x and take the limit as x goes to infinity. If I can show that this goes to 0, then that means this is going to be bounded by like 1 over x squared. And I know 1 over x squared is integrable in the limit. Well, as x goes to infinity, I've got infinity over infinity. How do I deal with infinity over infinity? L'Hopital. So I take the derivative of top and bottom. I would get 22x to the 21 over e to the x. All right, I still have infinity over infinity. And then eventually, we get 22 factorial over e to the x, which is 0. So eventually, we see that this ratio will tend to 0, so that if x is extremely large, e to the x is going to be much bigger than x to the 22. So this ratio here is going to be at most 1 over x squared. So when x is very, very large, this is decaying at least as fast as 1 over x squared. It's going to be okay. So I'm not worried about integrating at infinity. I am worried about integrating near 0. And the problem is I have an s minus 1. If s is less than 1, this is blowing up. And so the question is, what values of s is this okay for? Well, as x gets closer and closer to 0, e to the minus x, what does that look like as x goes to 0? It is just 1. So I'm not going to get any decay from this near 0 to balance an explosion here. So I need x to the s minus 1 to be integrable. So I need x to the s minus 1 to be integrable near x equals 0. So this forces s to be greater than 0. So as long as s is greater than 0, I can integrate. If s was less than 0, I had like 1 over x squared, that's going to blow up. So this makes sense so long as 0 is less than s is less than infinity. It turns out you can even have s be complex valued, and it's useful for a lot of things. All right, so what I want to do now is I want to show one of the nice properties of the gamma function. I want to show where this factorial relation comes from. So let's look at gamma of s plus 1. This is the integral from 0 to infinity of e to the minus x, x to the s plus 1 minus 1 dx. I'm going to integrate by parts. U, dv, du. I like going slow, explicit, write everything down. So I want to make things nicer. I want to decrease the power of the polynomial, so this is suggesting I should take u to be x to the s. And then du will be s x to the s minus 1. dv will be e to the negative x. And then v will be negative e to the minus x. So now when I look at my uv term, I get gamma of s plus 1 is uv minus the integral from 0 to infinity of v du. This will be negative x to the s, e to the negative x at 0 and infinity. And the minus becomes a plus, the integral from 0 to infinity of e to the minus x, x to the s minus 1 dx. And I have an s that I can just pull outside. Well, when I evaluate this at infinity, the e to the minus x kills the polynomial. When I evaluate it at 0, because s is greater than 0, I'll have 0 from this. So this term vanishes from the boundary. And we get gamma of s plus 1 is s gamma of s. And if you think back to factorials, n factorial is n times n minus 1 factorial. It satisfies the same relationship as the factorial. And so now we just evaluate a couple of small values of s by hand. The easiest value of s is to take s equals 1, and then you just get the integral of e to the minus x. That's an exponential random variable. And you see that the claim I made was correct, and that it really turns out gamma of n plus 1 is just n factorial. But what's nice now is because of this relation, you can extend the definition of the gamma function to be more than just the factorial function. It generalizes, it extrapolates the factorial function to all real numbers, or at least all positive real numbers. This is wonderful. And the reason it's wonderful is because the tools of calculus and analysis will be available. When you're studying a discrete thing, you really don't have much freedom to move. Everything is discrete. Calculus, it's the subject of continuity, of small motions and seeing what happens. By replacing the factorial function with an integral, we can actually use techniques to estimate how big this integral is. As an aside, this integral is exceptionally important. So let's do an application. Let's see if I can get this right. Let's say x is normal, mean 0, variance 1. Let's calculate the 2mth moment. So this will be the integral from minus infinity to infinity, x to the 2m, 1 over square root of 2 pi, e to the negative x squared over 2x. All right? This is the same as 1 over square root of 2 pi. I'm going to double and just go from 0 to infinity. X to the 2m, e to the negative x squared over 2 dx. Let's let u be x squared over 2. Then du is going to be x dx. So dx is going to be du divided by x. Well, x is 2u square root. So it'll be du over square root of 2u. Right? So my integration becomes 2 divided by, so it's the square root of 2 over pi. The integral u goes from 0 to infinity, because as x goes from 0 to infinity, u goes from 0 to infinity. X to the 2m, all right, it's going to become square root of 2u to the 2m, and then becomes e to the negative u, and then dx is du over square root of 2u. All right, square root of 2 over pi, u goes from 0 to infinity. All right, 2u to the 2m, the 2 kills the square root. We get a 2 to the m. We get a u to the m. Then we have a minus a half here, so we get a u to the m minus a half. E to the minus u du. And we have another square root of 2 down below, which kills the square root of 2 over here. All right, what does this look like? So we've got the expected value of x to the 2m is I can pull out the 2 to the m over square root of pi, and we have an integral from 0 to infinity of u to the m minus a half e to the negative u du. What does this look like? Yeah, it looks like a gamma function. Let's just rewrite it in a better way. 0 to infinity, e to the negative u, u to the m plus a half minus 1 du. So we get this is just 2 to the m over square root of pi gamma of m plus a half. What's the most important value of m to take? 0. What's the expected value of x to the 0 if it's a probability distribution? It's just 1. So 1 is equal to 0 is 1 divided by square root of pi gamma of 1/2. So gamma of 1/2 is the square root of pi, which is negative 1/2 factorial. If you use our interpretation of Gam of S plus 1 is S Gam of S, the number of ways of ordering negative half of a person when order matters is the square root of pi. This, of course, is a completely bullshit statement. You no longer can interpret this as negative a half factorial. It is a generalization. If you think back to the geometric series, 1 plus r squared, this is equal to 1 over 1 minus r. And we'll start after this. So if I add all the powers of 2, no, it doesn't go beyond negative infinity, wraps around and almost approaches 0 and gets negative 1. This can no longer be interpreted as that sum if the absolute value of r is greater than 1. Yes?
How do you work with like a negative factorial? What is that?
That is a question for the next time. It's not what you would expect. It's not the same as, in fact, negative integer factorials are actually plus infinity. And we can talk about that next time as to why that is the right definition for all of this.